In this lecture, we're going to talk about priority queue implementations. What we really mean is the underlying buffer that we'll be using to implement this priority queue. Priority queue is not your typical first in, first out data structure, even though it says queue. So queue is just a way of saying that you're queuing up these elements, but these queuing up requires the determination of the priority. So these priority could be a label that is attached to them that says, hey, this one has the highest priority. So that element becomes the front or the head of the queue, so on and so forth. So there are many ways to implement priority queue in Java. These implementation details will be dependent on obviously the Java collection, capital C collection. Let's just go through a different type of collection of elements. So let's just say if this collection of element is an unsorted list. So one example is the array list. This is in Java, but you can also come up with your own unsorted list, like in Python list. That is programming language agnostic. Now, why would a dequeuing requiring searching through the entire list? Well, think about this. Dequeuing based on the priority means that you have to find out from each element what is priority list because everything's unsorted. So, I mean, the worst case is O of n, right? You have to go through every single one of the elements inside this list to find your priority item. In queuing into an unsorted list, it's as simple as O of 1 because you should be able to enqueue any elements, right? Since this is unsorted towards the end of the list. So it would be in Java array list.add. So enqueuing is O of 1, but dequeuing worst case is O of n. Now, what if you have your array-based sorted list? So the array-based sorted list is similar to the unsorted list, but this one is sorted. The issue with this is that if your list is sorted, but this is array-based, every time you add something, let's say if you determine the location for this priority item is at 5, you insert that element at 5. But this is a fixed array-based sorted list, right? Let's just say you try to insert something, you're going to have to shift all of the elements, right, at that original location, one to the right. So there's that shifting motion there. That's why this is very expensive. It's O of n just to find the elements, and then the shift element is O of 1 times n number of times. In general, is O of n, and that is for enqueuing. Dequeuing into the array-based sorted list is the same thing. You dequeue something when you find it, then you have to shift all of the elements back. So there's that shifting back and forth things going on with the array sorted list. What if your underlying buffer is a sorted linked list? Linked list, remember, there is no array indexing. In order to find the priority items, you basically have to go through the entire list elements one at a time in a link fashion, next, until you find it. So this is O of n. Binary search tree, on average, O of log n steps for both enqueue and dequeue. This is true only if the binary search tree is balanced. This is the reason why the author says on average, because if the BST is not balanced, recall balance means that there is left and right. Let's just say you can have a lopsided tree like this, right? And obviously, enqueue and dequeue will not be O of log n because you're not carving your space out in half every time you move forward one level down. Instead, you would do O of n. On average, a binary search tree, because of the properties, right? That property guarantees on average O of log n for enqueue and dequeue. Just remember this enqueue and dequeue is with respect to priority determinations. Heap is a very important data structure. This is something that we're going to talk about next. This guarantees on average O of log n steps. This will be true if heap is implemented using some sort of tree, something like this. Every time you do a search for a guaranteed log n steps, you'll be able to find the maximum or the highest priority items, O of 1. This is the reason why we have what's called a maximum heap. We'll talk about this in the next section as well. On average, O of log n, this only applies for when you have tree structure, just like the binary search tree implemented. But if this is sorted, the insertion is going to be expensive. This is a various different priority queue implementation in the abstract. Let's go through the specific heap implementation in this coming chapter.